Hello and welcome back. The subject of this video is going to be introducing a new quantity. That new quantity is called momentum. Momentum is going to get the symbol P, and it is a vector quantity, meaning we need to have an arrow on it. It has both magnitude and direction. And momentum is equal to an object's mass times its velocity. So notice that it's a measure of mass in motion. Notice velocity is 0 for an object, then it has no momentum. If the velocity is anything other than 0, then it does have a momentum. And also notice that the direction of the momentum is the same as the direction of the velocity. Mass is always some positive quantity, so it won't change the direction part between velocity and momentum. So what kind of units will we have associated with momentum? Well, the units for momentum are going to be the units for mass, which are kilograms, times the units for velocity, which are meters per second. So the unit for momentum, kilogram meter per second, there's no special name for that. That's the units that we use to describe momentum, kilogram meters per second, standard in the metric system. So momentum gets at why you would rather be struck by a bee traveling at 2 meters per second than a Mack truck traveling at 2 meters per second. Measure of mass or inertia in motion. So momentum itself is a pretty easy quantity to calculate for objects if you know their mass and their velocity. I want to now go back to Newton's second law that we've been looking at since way back in chapter 4. And so recall that Newton's second law is the sum of all the forces, or F net, exerted on an object is equal to that object's mass times its acceleration. So when we add up all of the forces acting on an object, and we have to add them vectorially, then that sum of forces happens to be exactly the same as the product of the mass and the acceleration of the object. That's what Newton's second law tells us. Now notice that I can write acceleration from our definition back in chapters 2 and 3 as the change in velocity over the change in time. And so I'm going to go ahead and stuff that in to Newton's second law. The net force then can be written as the object's mass times the change in the velocity divided by the change in time. And now notice that if I tuck mass inside the delta symbol there, I will have Newton's second law then as the net force is equal to the change in the product of the mass and the velocity divided by the time. And notice that this quantity in parentheses now is our definition of momentum. So this is equal to the change in the momentum of an object divided by the change in time. And so Newton's second law can be written as the net force is equal to the change in the momentum divided by the change in time. Now this is actually the way Newton defined his second law, and more correctly, remember we're using delta symbols, but if you've had calculus, then the correct form and how Newton actually wrote down his second law is using differentials, dp dt. So this is actually how Newton wrote down his second law. This right here is a simplification of Newton's second law and really is only valid if an object's mass is not changing. So this that we've been using since chapter 4 is only good if the mass of the object remains constant. This form of Newton's second law, which written with differentials and exact, is in this form boxed in. This is the equation that is valid under all scenarios and how Newton represented his second law. So let's take this equation right here and let's now write it a little bit rearranged so that we isolate delta P. So delta P is equal to, how do I isolate delta P? Well, I have to multiply by delta T on both sides. So delta P is going to be equal to the net force supplied to an object times the time it's supplied. So this says the change in an object's momentum is equal to the net force being applied on the object times the time that that net force is applied. This is Newton's second law, just rearranged a little bit. Notice everything comes back to Newton's laws. Newton's second law says the only way to change the momentum of an object is to apply an unbalanced force for some amount of time. Notice that the units for momentum, as we saw up here in our definition of momentum, kilogram meter per second, can also be written as the units for force times the units for time, or a Newton second. And let's just check that a Newton second is the same as a kilogram meter per second. So a Newton times a second, Newton is a kilogram meter per second squared, and then we're going to multiply that by a second. Notice that this second in the numerator will take one of the seconds in the denominator, and so a Newton second is the same as a kilogram meter per second. So they're the same units. And the only way to change the momentum of an object is to apply an unbalanced force for some amount of time. So in the next video, we will then move on to look at scenarios under which there is no net force. In other words, the force being exerted on the system of objects externally is zero. Then under those conditions, there should be no change in the momentum for the system. And that'll be the subject of the next video. So we'll see.